In this video, we'll be rationalizing monomial denominators. When working with radical expressions, it's considered bad notation to leave a radical in the denominator of a fraction. The process of eliminating the radical in the denominator is called rationalizing the denominator. So if your denominator is a monomial, you want to multiply the numerator and denominator by a radical which creates a perfect square, cube, whatever, in the denominator. And then you want to simplify any radicals or perfects that you have. So let's rationalize the denominator of 4 over the cube root of 4x. Our thought process is we want to figure out what we have to multiply the denominator by so that we end up with a perfect at this point here in blue. We have a cube root, so we'll be multiplying by a cube root because the indices have to be the same for us to multiply. What would you have to multiply 4 by to get a perfect cube? Well, if you multiply 4 by 2, you get 8, and 8 is a perfect cube. The cube root of 8 is equal to 2. We want to do the same thought process with our variables. What exponent cancels with a cube root? An exponent of 3. So we want to have an exponent of 3 at this point. What do we need to multiply x by to get x to the third? We multiply it by x to the second. And then we can simplify that perfect. The cube root of x to the third is equal to just x. So the denominator makes all the decisions for us because that's where we're trying to eliminate the radical. It makes all the decisions. Now the numerator is going to go along for the ride. To keep the math legal, we know we have to multiply the numerator and the denominator of a fraction by the same thing, because essentially we're just multiplying by a fancy form of 1 right here. So let's multiply the numerator. Multiply what's on the outside together, leave it on the outside. Multiply the insides together, leave it on the inside. We get 4 times the cube root of 2x squared in the numerator. Then we want to try to simplify the radical. Can we simplify the cube root of 2? No. How about the cube root of x squared? No. So this is just going to come straight across. We get 4 times the cube root of 2x squared over 2x. Before we can be done, we want to look and see if we can simplify the fraction overall. Is there anything both on the outside that there can't be simplified? And yes, there is. 4 and 2 are both divisible by 2. We simplify and end up with a final answer of 2 times the cube root of 2x squared over x. In our next example, there's more going on everywhere, but our attention is focused on the denominator, and specifically the radical in the denominator. So we're actually going to ignore the 5 and just think, what would I have to multiply the square root of 2x by to get a perfect at this point? We're dealing with square roots, so we know that the radical we're going to be multiplying by is a square root. So 2 times what gives us a perfect square? Well, 2 times 2 is going to give us the square root of 4, which is a perfect. Same thing with the variables. What exponent on the variable is going to cancel with the square root x squared, what are we going to multiply x by to get x squared? We multiply it by x. We're going to be multiplying the top and the bottom by the square root of 2x. But since there was more happening in the denominator, I can't just finish the denominator right now. If we multiply what's on the outside together with our denominator, we get 5 on the outside, and then the square root of 4x squared underneath. In the numerator, since there are two terms, we're going to have to distribute. The square root of 2x times 8x to the third, 8x to the third on the outside, square root of 2x. And then multiplying square root of 2x times negative square root 32x is going to be negative square root 64x squared. We want to simplify any perfects that we have. Square root of 2x can't be simplified. The square root of 64x squared, that can be simplified. The square root of 64 is 8. The square root of x squared is x. And then in the denominator, we're going to have 5 times. We already know that the square root of 4x squared is a perfect. We designed it to be. Square root of 4 is 2. Square root of x squared is x. So that's 8x to the third square root of 2x minus 8x over 10x. Now we want to look at the fraction overall and see if we can simplify it. There's two different ways we can approach this. You can try to factor the numerator and denominator and then cancel common factors. I find that people have trouble with this, especially with the radicals. So another way to approach this is to break it up into two separate fractions and then simplify each fraction. In our first fraction, I see that 8 and 10 are both divisible by 2. So this becomes a 4, this becomes a 5. And I also have x to the third over x. I can simplify those by subtracting my exponents. So we're left with 4x squared square root of 2x in the numerator and just 5 in the denominator. With our next fraction, 8 and 10 are both divisible by 2. This is a 4, this is a 5. And the x's, well, they're going to cancel out for us, and we're left with minus 4/5. We get a final answer of 4x squared times the square root of 2x over 5 minus 4/5. Our next example is a cube root again. We want to figure out what to multiply the denominator by, so we end up with a perfect cube here. So what can we multiply 7 by to get a perfect cube? 7 is a prime number. Right, so there's only one 7 here. What do you have to multiply 1 7 by to get a perfect cube? Well, 2 more 7s. So we'll multiply by 49, and that will give us 343, which is the same as 7 to the third power. What exponent is going to cancel with our index of 3? An exponent of 3. So we need to ask ourselves, what are we going to multiply x squared by to get x to the third? We multiply it by x, and now we have a perfect cube, 343 x to the third under our cube root. The numerator is just going to go along for the ride. Multiplying our numerators together, we get the cube root of 49 x squared. And now we want to simplify. Can the cube root of 49 be simplified? No, there's not a perfect cube that's a factor of 49. How about simplifying the cube root of x squared? The answer is no again, since our exponent is less than our index. So our numerator stays the cube root of 49x squared. We know our denominators are perfect. We designed it to be. The cube root of 343 is 7, and the cube root of x to the third is just x. We want to look to see if we can simplify the fraction overall. Notice that there's nothing outside the radical in the numerator. You can only simplify things that are both outside the radical, so there's not going to be anything we can simplify here. Our answer is the cube root of 49x squared over 7x. In our last example, we have the square root of a fraction. We saw this when we were dividing radicals and working with our quotient rule. Notice that the fraction does not simplify. So the first thing we want to do is apply our quotient rule and break this up into the square root of the numerator over the square root of the denominator. We want to eliminate the square root in the denominator, so we want to ask ourselves, what are we going to multiply 5x by so that we get a perfect square? Five times 5 is going to give us 25, which is a perfect square. And then what exponent is going to cancel with our radical of 2, index of 2? Well, it needs to be x squared, so we multiply x by x to get x squared. Now we have a perfect square, 25x squared, under our square root. And we do the same multiplication in the numerator. Multiplying our numerator together, we get the square root of 15xy. We want to simplify our radicals. I'll start with the numerator. Can we simplify the square root of 15? No, there's not a perfect square that's a factor of 15. How about the variables? Our exponents are less than our index, so we can't simplify that either. Our numerator stays the square root of 15xy. In the denominator, we know we have a perfect. Simplifying the square root of 25x squared, we get 5x. You want to look to see if you can simplify the fraction overall. Just like the previous example, there's nothing outside the radical in the numerator. Therefore, we are not going to be able to cancel anything with our denominator that is outside of our radical. Our final answer is the square root of 15xy over 5x.